All right, let's dive in. Today, we're not just solving a math problem. Nope, we are on a mission to decode a puzzle, one that's hidden inside something called a polynomial. Let's get to it. Okay, take a look at this. At first glance, I know it might look like a totally random jumble of symbols and numbers. It's a cubic polynomial, and yeah, it can look a little intimidating. But what if I told you it's not random at all? Because that's exactly what it is. We're going to treat this thing like a secret code. And our job right now is to learn the rules to crack it. So where do we even begin? Well, you always start with the basics. So first things first, let's get the rules of the game straight. What in the world is a polynomial anyway? Here's the most important rule of all. A polynomial is basically just a string of math terms, where the powers on your variable, the x, have to be nice, friendly, whole numbers, like 0, 1, 2, 3, and so on. No fractions, no negative numbers allowed as powers. That's the key. And this right here makes it crystal clear. Over on the left, you've got your valid polynomials. See how all the powers are whole numbers? 3, 2, 1, 6, 4, 2, all good. But on the right, those are imposters. The first one has a square root of x, which is really x to the power of 1/2. Breaks the rule. The second one has 8 over x, which is the same as x to the power of -1. Rule broken again. Easier, right? Okay, now let's look at the anatomy, the blueprint of a polynomial. Every piece has a name. The individual chunks that you add together are called terms. The numbers out in front of the variables, those are your coefficients. And probably the most important part for us is the degree. That's just the biggest power you see anywhere in the expression. And that degree is a huge deal. It actually gives the polynomial its family name. A degree of 1 is called linear. A degree of 2 is a quadratic. And a degree of 3, like the puzzle we started with, is called a cubic. That's a really important clue for our mission. So we know the rules of the puzzle, but what's the solution we're looking for? Well, it's a quest for something called roots. So what's the goal of this whole quest? It all comes down to this number right here, 0. We are literally searching for the special magic values of x that will make that entire long expression equal to 0. And these magic values have a name. We call them roots, or sometimes you'll hear them called zeros. A root is just a number that, when you plug it in for x, makes the whole equation work out perfectly to 0. Finding the roots is cracking the code. It's the solution to our puzzle. And here's a massive clue. It's like a map for our quest. The degree of the polynomial tells you exactly how many roots you should be looking for. So a quadratic with a degree of 2 is going to have 2 roots. Our puzzle is a cubic, degree 3, so that means we are on the hunt for 3 roots. We know exactly what to look for. Okay, mission accepted. We're looking for 3 roots, but how in the world do we actually find them? Let's get our code-breaking tools ready. The number one strategy is to factorize. You basically take the big, clunky polynomial and break it down into smaller, bite-sized pieces that are all multiplied together. Then we use this awesome little rule called the zero product property. All it says is that if you multiply a bunch of things together and the answer is 0, well then at least one of those things had to be 0 in the first place, right? This lets us solve each tiny piece on its own. Let's watch it work with an easier example, a quadratic. We've got x squared minus 4x plus 3. Turns out we can break that down, or factor it, into 2 chunks, x minus 3 times x minus 1. Now, if that whole thing equals 0, it means either the first chunk is 0 or the second chunk is 0. And those are super easy to solve. So we get our 2 roots, x equals 3 and x equals 1. Done. Now, that was nice and clean, wasn't it? But what happens when you look at a big one, like our original cubic puzzle, and you can't just see the factors right away? We're going to need another tool in our toolkit for when things get tricky. This is where the hit and trial method comes to the rescue. Now, it's not just random guessing, it's smart guessing. You look at the very last number in the polynomial, the one with no x. For our puzzle, x cubed minus 6x squared plus 11x minus 6, that number is -6. Any whole number roots have to be factors of -6. So we can test numbers like 1, -1, 2, -2, 3, and if we plug 1 in and the whole thing equals 0, bingo, we've found our first root. Okay, but plugging in all those numbers sounds tedious. There has to be a faster way, a shortcut, right? Oh, you bet there is. And it's called synthetic division. Exactly.
Testing all those factors one by one works, but come on, we need something more efficient. And that shortcut we just mentioned, synthetic division, is an absolute game changer for solving these puzzles quickly. So what is synthetic division? Think of it as a super fast way to check if a number is a root. It's a slick, streamlined process that quickly tells you what the remainder is when you divide your big polynomial by a little piece like x minus a. And trust me, that remainder is everything.
The process itself is surprisingly simple. You just take the root you want to test, let's say the number 2, and you write down the coefficients from your polynomial in a line. Then it's just a simple pattern. Bring down the first number, multiply it by your test root, add it to the next number, and repeat. Multiply, add, all the way to the end. And here it is, the magic moment. That very last number you write down at the end of the process. That's the remainder. And if that number is 0, you've done it. It is 100% confirmation that the number you were testing is a root of your polynomial. No guesswork, just a clean, fast answer. So, that thing that started out looking like an intimidating, random string of symbols, we can see it for what it really is now. It's not random at all. It's a perfectly structured system with its own rules, its own parts, and most importantly, solutions. Its roots that are just sitting there waiting for us to find them with the right set of tools. So we cracked the code, we learned the language, we figured out the goal, and we found the tools to get to the solution. The biggest takeaway here isn't just about polynomials. It's about seeing that a complex problem can almost always be broken down into simple, manageable steps. So the real question to leave you with is, now that you know the rules of the game, what other puzzles out there are you ready to solve?